Okay, we're going to continue on here, talking about nuclear chemistry. So last time we talked about different types of radioactive particles. We talked about balancing nuclear equations. So remember that when we have a nuclear equation, we basically balance it a little bit different. We're looking for all of our mass numbers up on the left-hand side of the equation to equal all the atomic numbers. I'm sorry, equal all the mass numbers on the right-hand side of the equation. And in terms of atomic numbers, which are our bottom number, they do also need to equal each other. So the atomic number on the left needs to equal the atomic number on the right. So um, that's basically how we balance nuclear equations. Again, the idea here is because there's no conservation of elements, we do not balance it like a normal chemical equation where we have the same elements from beginning to end. Here, because we basically change things that are in the nucleus, we form new elements. And because of that, we balance it through mass number and atomic number. Remember that there are several different types of particles that we talked about in nuclear chemistry. There are alpha particles, which are the alpha symbol for two, or you can do the helium symbol for it as well. We also have beta particles. Beta particles can use the beta symbol, or you can use basically an E for an electron. We also have positron particles, which will use really the same symbols there as the beta particles, but it is +1 there on the bottom. Or it could also do this. There's also neutrons, which use an end. There's protons, which use a P or a hydrogen, basically. So we got alpha, beta, positrons, neutrons, protons. And again, these are some different particles that are very common in these sort of reactions. Once again, because we are sort of changing protons to neutrons or neutrons to protons, um, that is where these particles sort of get generated from, is sort of the leftover part, if you will, that comes off in terms of these reactions when we do those transformations. So remember that if you have things in words and it says it goes through some type of decay, like alpha decay, or it emits an alpha particle, all those sort of words means that your alpha particle should be sort of on the product side. And again, if it goes through any type of decay process and it tells you it's beta, bless you, all right, whatever it may be, positron, those particles can end up on the product side. There are a few situations or a couple situations where you can end up with a particle on the reactant side. And usually that is an electron capture. So if you have some type of electron capture, that electron should be on the reactant side. Also, again, if you sort of bombard something, say with neutrons or something like that, that also means the neutron should end up on the reactant side. So either an electron capture or some type of bombardment will have those particles on the reactant side of the arrow. Any type of emission or decay process through some type of emission, those particles will end up on the product side. Remember that it is the atomic number, which is our bottom number. That's really where you want to kind of go first at if you have an equation, maybe something's missing, or if you're just kind of trying to figure out what it forms. The atomic number really will tell you what element is going to be formed as a result of this sort of decay process. Remember that the atomic number is the number of protons. Every element on the periodic table has a different atomic number. So again, if you know the protons, the atomic number, you will know what element is being formed in this case. Um, and then mass number as well. You just want to make sure that you add them up correctly. In addition, if there happens to be a coefficient in front of something, like 3 neutrons, you do have to multiply the 3 to both of those guys. Obviously, the bottom one is not that bit important, but the top one is there in terms of the mass number. You need to make sure that you multiply it because, again, the coefficient is what it normally means that you don't have just one of these, you don't have two, but you have three neutrons, which again would give you sort of a mass number up on top there of three. So you want to make sure that you adjust it accordingly. We then talked about stability, and one sort of big way that we look at stability, and that is the N to Z ratio. And that's basically our neutrons to proton ratio. And there is this sort of belt of stability, this sort of valley of stability, and that is where things are sort of have a nice sort of stable arrangement with their N to Z ratio. And again, if we find that we are kind of too high or too low in terms of the valley, you could either find yourself kind of in this position. We do want to kind of move ourselves towards that valley of stability to become more stable. And the way it does that is the thing will go through some type of radioactive decay. And depending if you're too high or you're too low as to what will happen, if you're too, excuse me, if you're too high, you will do a beta decay to kind of bring yourself down. And if you're too low, again, you have the option there of one or two things, either a positron emission or an electron capture, which, as we saw in the example we did last time, will yield you the same product at the end, regardless of which one you're doing. And again, that should bring the ratio not always perfect in terms of stability, but it should move you closer to that kind of more stable ratio. Remember, it is sort of based off of the atomic number. So if you got something like 1 through 20, the good ratio there is 1. If you got like 20 to 40, you're looking at like 1.25, maybe 40 to 80, 1.54. And remember that anything above 83 basically is going to be radioactive and stuff. So um, we were, as we talked about, going to kind of use these ratios, 1.50, I think, as sort of pretty hard cutoffs, they're either above or below. Again, as I mentioned before, because the cutoffs sort of roll one into the other, you'll sometimes see in book problems sort of a grayish area if you're kind of in the area of those guys. But we'll try to avoid those guys and just kind of go either too high or too low. In the case of that, as we talked about, we don't continue the decay process in these type of problems until we get something that's perfectly stable. We just kind of do the first sort of decay process and sort of indicate what happens. The other things that you can sometimes look at in terms of helping you understand stability as well, sort of the best condition is where we have, in terms of protons and neutrons, we have even of both. So we have even protons and even neutrons. That's a pretty good sort of arrangement for stability. We have the most stable nucleuses with that arrangement. Kind of the worst in terms of stability is odd and odd of each of these things, and there's only like 5 of them not so good that are stable in that arrangement. So having one of those things or both of those things at least even is really good for stability. But again, if they're both odd, it's not so great, turns out, in terms of stability. Any questions on any of that stuff there? All right, so we're going to continue on and talk about a decay series. And a decay series is a series of radioactive decay processes which occur basically one right after each other, usually starting with something that is unstable. And it will continue to sort of go through this decay series, usually until it kind of hits something that's pretty stable and kind of happy at that point along the way. Remember that sort of what you start with is sometimes referred to as the parent nuclide. Nuclide is, again, a fancy way of saying the nucleus and basically the isotope that you're looking at, basically. And what is formed is usually the result of a daughter, as the daughter nuclei. Again, they will continue this sort of process, like I said, until they kind of hit something that is relatively stable. And there's one of two ways that you could kind of do this. You could kind of really do a decay series and want to try to figure out what's happening the exact same way that we do sort of balancing equations in this situation. You basically could just write the equations and figure out what you get. If you are maybe just interested in like what you get at the very end of the process at the very end, and it's all like alpha decays and beta decays that's happening, and really, like I said, all you're kind of interested in is sort of what you get. For every alpha decay that it goes through, you would subtract 4 from the mass number and 2 from the atomic number. And then for every beta decay it goes through, you basically could just add 1 back to the atomic number on the bottom. So if you're again just kind of looking at the end product and you just want to kind of get there quickly, and like I said, everything is just an alpha and a beta decay. Obviously, if there's other type of decays that are happening in there besides alpha and beta, you would have to adjust, obviously, if it was a positron versus something else. Um, you can kind of just do the math part of it. So if we look at, say, whoops, now we do it here. So if we look at, say, uranium 238, and let's just say we'll do the short series here. It goes through an alpha, a beta, an alpha, an alpha, and an alpha, and it, as we will see shortly, it actually just continues on from that process. So if we wanted to sort of figure out what is happening or what we get sort of after each of these sort of decay steps, we obviously would go to the periodic table and we would find uranium, which is number 92 there. And that would give us basically our starting move here, which is 238, 92. So the first thing that's going to happen is it's going to go through an alpha decay. So again, since it is going to go through an alpha decay, that means that the alpha particle will be on our product side. And once again, you can use the helium or you could use the alpha symbol, whichever one that you like. So remember, we're just going to do like we did with balancing equations here. So I got 92 on the left and 2 on the right. Which means my missing atomic number in this case is going to be 90 to get me to 92 on both sides. Again, I could go to the periodic table, which is your friend when you're doing these things, and number 90 is TH. In terms of my mass number up on top, I got 238, and I got on the left and 4 on the right, which means, and again, to make them equal to each other, 234 looks like a winning move there. Now, this is sort of our first step in our decay process. This is what will actually be formed. And in a decay series here, we basically just take what is formed in the previous step, and that is what we start with next. So we would then take this guy down, and now this guy is going to go through a beta decay. And again, a beta decay in this case means that our beta particle should be on the product side. Once again, in this situation, you could use the E for the symbol rather than the beta symbol. So in this case here, we need to go actually 1 more, right? 91 and negative plus -1 is 90. So that moves us to PA in this case. Up on top is 234 on the left and 0 on the right. So our mass number here is going to kind of stay the same. As we talked about last time, even though the mass number sometimes does stay the same, remember what's kind of happening a lot of times in those cases is like a proton is being converted into a neutron. So in terms of the mass number, although we lose a proton, we add back a neutron, it basically ends up the same number at the end. So next thing that will happen is this guy will then continue down the decay process here, and he's going to go through a beta decay. And again, that's going to put our beta particle on our product side. Once again, we got to go up 1 because that's a -1. And that's going to take us to 92 at this point, which is going to take us back to uranium. And now we're at uranium 234 here. Again, the uranium 234 will then go through a alpha decay or 2 alpha. Here, we're going to take 2 off. That's going to take us to 90. 90, as we saw earlier, is TH. And 234 minus 4 will get us to 230 in this case. And again, just continuing on, one more alpha here. Although we are forming the same elements along the way here, we really are not. We are forming some different isotopes of these elements, right? So the TH that we had earlier was TH technetium 234 as opposed to technetium 230 at the end here. This goes through an alpha. And again here, 90 on the left, 2 on the right. That's an 88, I believe. Should get me there. And 88 there is going to be RA. And up on top, we got 234. I'm sorry, 230 minus 4, 226, I believe. Gets us there. And lastly, here, we're going to go through one more alpha particle, 226, 88, and our alpha. And again, up on the bottom, 88 on the left, 2 on the right. It's going to take us to 86. And 86 is going to be there, looks like RN. And 222, I believe, there up on top is where we should end with in terms of this. So our final one there, I'll write a little higher in case it's getting cut off there. Go. That's our final product. So you can see here, you basically could just do balancing equations in a decay series. Again, whatever you produce will become your starting on the next one. Like I said before, if you're really just interested in kind of where you end up at the end of this process and everything was really just alpha and beta decays, you basically could just start with your mass number and your atomic numbers. And when we look at our alphas, we got 1, 2, 3, and 4 of them. So every alpha particle, we're going to subtract 4, and there's 4 of them, so that's a 16 off of that. And in terms of the bottom there, we're going to take 2 for every alpha. So 2 times that is 8. Now for every beta particle, we're going to basically put 1 back. So we do like a +2 on the bottom. And obviously here, we should hopefully end up with 2, 2, 2. And again, we end up with R 86 in this case. Yeah. And obviously at that point, you could go to the periodic table and find 86, and you should end up obviously with what you get at the end. So if you're not, again, interested in the entire process there, you could kind of do it just the math way and get yourself to the end product. Any questions on that there? So decay series, basically just same idea as balancing equations. Products become your reactants in each step. Any questions? Okay. All right. And here is uranium-238, which is what we did. We did just the first part of it here through here, I think. And as you can see, it will continue. And actually, one of the things, as I mentioned before, in terms of radioactive decay, is not always 100% predictable as to what you get. And you can see here, it can oftentimes, this guy branch out into 2 different sort of pathways. They do usually will all end up in the kind of the same spot there. I end up there at lead 206 as a stable isotope. But again, that's one of the things that's very common in radioactive decay. You don't always get the same thing every single time that it sort of goes through a decay process. You sometimes get some different products along the way. All right, the next thing we're going to talk about in terms of radioactive decay is our favorite thing ever, which is kinetics. A nice throwback to the first chapters we talked about. So, in terms of radioactive decay, it follows kinetics, and it follows a specific kinetics. It follows first order kinetics. And so, basically, it will follow our normal first order kinetics like we learned about the beginning of the semester. Remember that first order kinetics basically has 2 main sort of formulas that go with it. Integrated rate law, the natural log of A, is equal to the natural log of A naught minus KT. And it also has a half-life that is the natural log of 2 over K. Now, a couple of things about it in nuclear chemistry. Honestly, it is the exact same formula that we used in kinetics. It's the exact same first order equation. The difference, though, in nuclear chemistry is sometimes they like to use some different symbols for things. So instead of A's, they sometimes would like to use N's to refer to as nuclides. But it basically means the same thing. So sometimes, again, you'll see it like natural log of N is equal to the natural log of NO minus, and sometimes here for the K, you may also sometimes see lambda used for the constant rather than K. Although I think our book uses sort of the regular sort of formula, but sometimes you may see it a little bit different as well. Now, a couple other things that are a little bit different than maybe we normally think about. First off, this is our sort of final as normal. This again is our initial. Now, one of the things is going to be very different than maybe how we sort of did kinetics in the first chapter. In the first chapter, when we did kinetics, we basically always kind of use concentration in those spots. And you can definitely use concentration, obviously, as we did in kinetics, but you could really use any unit you want in both of those spots. So it's very common in radioactive decay. Maybe it's grams and grams that go in there, or maybe it's milligrams and milligrams. Also, rates of radioactive decay are commonly used as kind of concentrations. So you may have something like counts per minute or counts per minute, and in terms of a rate that's used. So as long as like our traditional sort of A spot there, as long as the units are the same on both sides, you can basically put anything you want into that equation. It does not have to necessarily be molarity like we kind of did in the first chapter. So again, works very much the same way, but you will definitely see some different units kind of being thrown into those A spots there that are not molarity. And again, as long as they're the same unit, you're all good. The K here, or even the lambda, is not referred to in nuclear chemistry as the rate constant. It is sometimes referred to usually as the decay constant. Kind of the same thing, just kind of a different name that is sort of given here. T here is also, like we talked about in kinetics, it is time, remember, right? So that is a unit of time. Also, a couple important things that we've talked about previously in kinetics. This back part of this formula here, in terms of time, you do want to make sure that they are in the same units, right? So if one's in seconds, the other one needs to be in seconds. If one's in minutes, the other one needs to be in minutes, hours, years, whatever it may be. Still the same thing as what we talked about with first order kinetics in the kinetics chapter. Uh, the decay constant is also 1 over some unit of time, 1 over seconds, 1 over hours, 1 over years. You know, it is that reciprocal sort of unit of time is the rate constant or the decay constant that is commonly used here. Probably more so than what we saw in sort of kinetics chapter. Definitely in this chapter, because it involves basically radioactive decay, it is very, very common that you are given the half-life and you are not given the decay constant. So it is probably more common in this chapter than maybe we saw in the previous chapter that you do have to use the half-life equation and the integrated rate law sort of together a lot of times in problems. And that is usually because you will use this guy, the half-life equation, to figure out the decay constant so that you can then use the integrated rate law to figure out what you're actually trying to calculate. So it's very common that both of those are used sort of in tandem a lot in this sort of situation. Now, in addition, we have our normal sort of plots, our first order plots, right? This is our concentration versus time decreasing with time. This is our y equals mx plus b version of this, right? Where we rearrange this. actually like this. And that's our y is equal to mx plus b. Just like in kinetics, if you have some type of graphical display, this will give you the decay constant, right? So the slope here is equal to minus the decay constant, just like we saw in kinetics in this particular case as well. And again, you can see in some places they will use lambda for the decay constant. Once again, I do think our book now uses, I think it does use K, but again, if you use lambda in this thing, it is the decay constant. The good news about radioactive decay and kinetics is you can't choose the wrong one. It's always first order. So that's the two that you should always choose. So you could identify it as like a radioactive type thing happening in decay process. You should definitely be rolling with the first order kinetics. We obviously would use this just like normal, that we could solve for anything there, final sort of concentrations or counts per minute, initial time. Now, when we look at half-lives, again, that is obviously the time it takes for half of whatever you had to basically disappear. And things are different types of emitters. There's alpha emitters, beta, gamma emitters. Um, and they have different sort of time. You can see here, uranium 238 takes a very long time for half of it to go away. And none of us will be there for any of it. Some of it is super fast, right? So these are within seconds. Your thing's pretty much gone at that point very, very quickly. Some are days and so forth. Obviously, the longer the half life is going to hang around a little bit for a longer period of time. The shorter the half life, it should obviously be not as radioactive, much quicker period of time. So, in terms of applications, again, typically if you're doing anything with a medicine, you would want something with a much shorter half life, obviously. Otherwise, your follow up appointments in a lot of years down the road. And obviously, just naturally things do have pretty long half lives. Um, if you're working in the laboratory, you may want things that are reasonable so that you could kind of continue on with your experiment. Just to give you an example, I used to do work with copper 64 and copper 68. Copper 64 had a half life of 13 hours, which means, fairly soon it wasn't all that bad to be around. Copper 68 had a half life of 3 days, which was a much, much longer period of time you had to wait for things to kind of get not so radioactive if you wanted to continue on and do things with it. So there are some advantages to some versus the other. If you need to follow the radioactivity for a long period of time, you would want something with a little bit longer of a half life, right, than something that's much shorter. All right, so let's take a look at one here. If you have 1.35 milligrams of plutonium 236, how much will remain after 5 years? And we'll give you the half life there is 2.86 years. So why don't you take a few moments and calculate up what you should have left? Okay, let's take a look. Again, like I said, the good news is it's always first order here with this stuff. So we basically know the equations. You could use the exact same equation as before. You don't have to use any fancy symbols. It all works out the same. We got our half-life is going to be natural log of 2 over k. So in this particular case, we have, which would be our initial 1.35 milligrams. We're looking for how much remains at the end. And we have our time, which is 5 years. Once again, we just kind of check off, we got that, we are looking for that. So as I mentioned before, very common in these type of problems, we are missing the decay constant in this case, but we do have the half-life, so that can be used along with our half-life equation to get to the decay constant. So that would be k is equal to the natural log of 2 divided by the half-life. That would be the natural log of 2, which is that 0.693 number, divided by 2.86 years. That's going to get us here, natural log of 2 divided by 2.86. Going to yield us a 0.242. The units here are reciprocal years, which is good as it should be reciprocal unit of time. Also good is the unit of time here. Remember, again, we do want these guys to have the same time unit. And in this case, they are both years, so we can put it in without any problems of units not canceling. That gives us the natural log of A is equal to the natural log of 1.35 minus RK. We just calculated there 0.242 reciprocal years and our 5 years in this case. Again, the years will cancel. And if we clean up everything on the right hand side, we're looking at natural log of 1.35 minus our decay constant times 5. That's going to get us the natural log of A is equal to minus 0.91169. We're going to E both sides, right, to get rid of that. And that will get us how much is left over here after 5 years. And it looks like perhaps 0.402. The units of this will end up being the same units as the initial guy there. So these again are milligrams in this case. Any questions on that one there? Nice little first order kinetics review there. All right. Then let's take a look at another one here. Radon 222 is a gas suspected of causing cancer, assuming no leakage or no loss or gain from leakage. If there is 10.24 grams in the house today, how much will be there in 5.4 weeks? Half life is 3.8 days. Okay, so taking a look at this again, we're going to roll with our first order kinetics here. And again, in this case, we got there our initial, which is 10.24. We're looking for what we got left over. Our time in this case is 5.4 weeks. So once again, we are missing the decay constant. We do have the half-life given to us, so we'll use our half-life equation here to solve for our decay constant. And I'll get natural log of 2, 3.8 days. And if I do that there, looks like natural log of 2, 3.8. Looks like we end up with 0.1824 reciprocal days. Now, again, when I put it into these two, I do need to make sure we're in the same units. And I have this one in days, this one's in weeks. So that is not going to work together. So we do have to do a conversion. And really, if you wanted to, you could convert the half-life into weeks and then just did it that way. Or you convert, obviously, like I'm going to do our weeks into days. So 1 week is 2 days. No, 7 days. Wishful thinking. There you go. 37.8 days in this case. Now we have both of these guys in the same unit, so everything should cancel out correctly. We'll end up with our natural log of A is equal to our natural log of 10.24. And obviously, if you did the other conversion, you'll have maybe some slightly different numbers. Hopefully, the head and answer should be the same. We'll end up with 0.1824 reciprocal days and our 37.8 days here. Again, days going to cancel out. Going to get us here natural log of 10.2. Try the right number. Natural log 10.24 minus 0.1824 times 37.8. Going to get us natural log of A is equal to minus 4.5684. Again, going to E kind of both sides there. Going to get us a final concentration here of, looks like 0.0104. Whoops. Uh, these are actually grams in this case. There you go. Any questions on that one? Yeah. Are you talking about like, are you talking about the weeks and the days? Is that what we're talking about? It doesn't really matter. You can do it either way. They both in the end should give you the same answer. You may not get the same like decay constant along the way, depending if you did weeks or days. But in the end, with rounding, it should be pretty much the same answer along the way. So, but they definitely has to be the same. They can't be different. Otherwise, again, they won't cancel out. Yeah. Other questions? All right. Now, obviously, what we've been doing there is very similar to what we did in the first chapter there. We could also use this first order kinetics to do what is sometimes referred to as radio dating. It basically is solved the exact same way as what we've just been doing. The only difference is usually you'll be solving for time in this case to figure out how old something is. So there's radiocarbon dating, where we can look at sort of how much carbon 14 has sort of decayed over time into nitrogen. The half-life for carbon 13 is 5730 years. We can also do uranium 238 dating, in which it decays down into lead. And sometimes this is how much lead is there versus what we started with. But that also has a half-life of 4.51 times 10 to the minus, 10 to the 9 years in this case. So if we take a look at one here, if we have an ancient skull, and it gives, this is a rate of radioactive decay. So this is not like a concentration necessarily. It's not like grams and milligrams. It is, though, a rate of radioactive decay. And what the sort of abbreviations mean here, this is disintegrations per minute per gram of carbon. So this C here is actually carbon. It is not degrees Celsius or anything like that. So the C in this case is carbon. The importance of that is it tells us that basically we're doing carbon 14 here, and that is going to be the half-life that we would want to use, which is the carbon 14 half-life in these type of problems. So for any type of rate of radioactive decay that's involving carbon, you may be doing some type of carbon dating, and really your half-life there is 5730 years is what you want to use. If a living organism has 15.3 disintegrations per minute per gram of carbon, we want to know how old is this skull. So once again, this is just a kinetics problem. We still radioactive decay, so we definitely know we are going to be using first order in this case. And as I mentioned earlier, we can use rates as our concentrations. So our initial concentration is usually things when you first start out, you're living, right? So that is living in this case, right? So it would be 15.3 disintegrations per minute per gram of carbon. Also should probably have a higher rate of radioactive decay, a higher count because it's fresher, right? So it hasn't gone through a lot of half-lives. So it should be giving off a lot more radioactivity than the guy at the end, which in this case would be the ancient skull, which has less radioactivity coming off because it's gone through some half-lives at this point. So it is not going to be giving off as much radioactivity. And that is our 4.5 in this case. And again, here we're looking for, in this case, really how old it is. So much like in the previous problems, we are missing sort of our decay constant, and that is where our half-life is going to come into play. That is also where understanding that that is carbon rather than Celsius, that you understand that you should use the half-life of carbon. If it happened to be some other unit or some other element, you would want to use the appropriate half-life for it if it wasn't grams of carbon. So in this case here, we are again going to use our half-life equation to figure out our decay constant. So rearranging it gets us our natural log of 2 over our half-life. And that's going to get us the natural log of 2 divided by our 5730 years. And in this case, we will end up with natural log of 2 divided by 5730. End up with 1.21 times 10. Takes the minus 4. 1, 2, 3, 4. Minus 4 reciprocal years in this case. Now that we have that, we pretty much have everything that we need to solve this. We could go into it. So natural log of our final 4.5 equals the natural log of our initial 15.3 minus our k that we just got there, 1.21 times 10 to the minus 4 reciprocal years, and our time in this case. So again, natural log this, take this to the other side and subtract it. So we're going to do a natural log of 4.5 minus the natural log of 15.3. That's going to get us a negative 1.223775 is equal to negative 1.21 times 10 to the minus 4 reciprocal years in time. Gonna divide that obviously to the other side. And that's gonna get us here a time that is about 10,114 years in this case, yeah. So fairly old, I would say, about 10,000 years old. Any questions on that there? Let's take a look at one more here, I think. All right, so we have dated a civilization here to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon in a grain of rice that is found at the site? So take a moment there, see what you come up with. All right, let's take a look. Again, we're going to roll with our first order here. We have our time here, which is 15,600 years. We have a living sample, so that seems initial there. And again, this is another unit of radioactive decay, so this is 20 counts per minute per gram of carbon. And we're looking for how many counts we got going on at the end. And once again, here we do need to get the decay constant. Again, because this is carbon, we will use the same half-life as in the previous one, 5730, which will yield us the same decay constant, 1.21 times 10 to the minus 4 reciprocal years. So again, we should end up basically with the same decay constant as we had on the previous one, since they are both carbon. That is all we need here. So we're going to go natural log of A is equal to our natural log of 20 minus our 1.21 times 10 to the minus 4 years and our 15,600 years. Again, our unit of time are the same, so they cancel out. You do want to, again, watch that and make sure they are. And we're cleaning up the right-hand side there. Natural 20 minus 1.21 to the minus 4 times 15,600. Going to get us a natural log of A is equal to 1.10813. We're going to E both sides there. And we are going to end up with a 303. And again, the units would be the same as the other counts per minute per gram of carbon. This again does make some sense. We did end up at least with a smaller value than we started with. Again, because at this point it's gone through several half-lives probably, or some half-lives and some decaying, which means it should not be as radioactive as it was at the beginning, and we should not be giving off as much radioactivity here at the end. Any questions on kinetics and radioactive decay? Good news is, like I said, first order stuff, yeah, so not too bad. Yeah, that's good. All right, we're going to lay it up there for now.